This time we will learn about the MOSCAP device. MOSCAP device is important because before we understand the MOSFET device, we have to first know about the MOSCAP device. The MOSCAP is first, MOS means metal, oxide, semiconductor. And the cap means capacitor. So the MOSCAP means the capacitor which has a metal oxide semiconductor structure. So I draw the MOSCAP structure. So this part is semiconductor. And this part is oxide. And this part is metal. So we call that MOS capacitor. So we call this MOSCAP. In MOSCAP, we can use this M part in heavily doped polysilicon instead of metal. And we call this semiconductor, and we also call this part a substrate or body. So by this device, we can use the device like a capacitor. So let's draw about the MOSCAP Venn diagram. Before we drawing this Venn diagram, we will use P-type substrate, P-type semiconductor, and we also use the heavily doped anti-polysilicon instead of metal. In flat band condition, first we draw a vacuum level energy. And second, we can draw the dioxide. And after that, we draw the substrate and gate. We use both the semiconductor, so this valence band and conduction band gap is same for gate to substrate. But the Fermi level is different because in the gate side, it is a really heavily doped N-type semiconductor. So we can draw the Fermi level like this. But in this case, it's just a P-type doped, so we can draw the Fermi level like this. So this is a flat band condition Venn diagram. And let's draw the thermal equilibrium state Venn diagram. As you know, if the thermal equilibrium state, the Fermi level is always constant. So we can draw like this. It's a gate side. And the substrate size Fermi level is constant with gate side. So in this case, the valence band and conduction band is go up. But the electron affinity and ionization energy is offset, so it is also same level when it divides, whether it divides is summer equilibrium or not. So the band is bending like this because it has to keep their energy like this gap and this offset. So they also keep their offset. So the dioxide goes up and bending like this. So it's a summer equilibrium Venn diagram state. And we will see the three states which give a bias to this device. The first is depletion, second is accumulation, third is inversion. So let's see about depletion first. The depletion is similar with the summer equilibrium state, but it doesn't have to keep their keep their Fermi level constant. If the bias conducts, it can draw it like this. It doesn't matter even if the Fermi level is not constant, because we already conduct the bias for this state. And we used the N-type doped semiconductor. So the P-type doped. So in this case, in this, if we see this surface, the electron is combined in this surface. And in the p-n junction class, we already learned about that, the depletion region. In the p-type, it has minus ionized and it also have a fixed charge in minus charge, and there has also gained minus charge electron, so the depletion width is more wider. So if we draw the charge density graph, we can draw like this. and by the surface has a minus electron in here. So as the result, the other side of this part gained a little bit plus charge. So we can draw it like this. So this surface and this surface are same charge, and the pole is reversed. It's a depletion. And let's see the accumulation state. If we give a bias like if we give a bias from gate side to minus and substrate side to plus, we can draw the energy band diagram. Like this. Because we learned that if the minus bias part goes up and plus bias part goes down. So we can draw the band diagram like this. And for this state, the hole gains from this surface. So we can draw the electron, we can draw the charge density graph like this. There has gained a plus hole charge, and in this part we can gain a minus charge in here. The accumulation means we already doped this type of p-type, and in the surface we accumulate the same polarity charge, so we can this state called accumulation, because in p-type doped the major carrier is whole. So we call this state accumulation. And inversion is a different. Before explaining the inversion, let's see the depletion state again. Just before we draw the depletion state, but if we give too much bias to this device, the depletion rate is get higher and higher. So in this case, we can draw the Venn diagram like this. And the Fermi level states are like this. But let's see this part. In this part, the Fermi level goes up really higher. So in this case, we can't call this a p-type. It conducts like a n-type case. So we can't call this part like a p-type. So we can this situation a inversion state. If we make a inversion state, we in this surface, the minus charge, electron charge accumulated like this surface. So we can draw the charge density like this. So why we call this inversion? We already doped the p-type semiconductor. So the major carrier is hole, but it doesn't accumulate this hole in this surface. It has more than electron in this surface, and in this surface, compared to this part, we can't call this energy band diagram like p-type. The Fermi levels is more goes up to conduction band, so it conducts like a n-type. So we can call this state inversion. So we just saw the 5 case for the MOSCAP design. And last, we will see the CV characteristic. As I mentioned, this MOSCAP device can control like capacitor, so we can discuss about the conductivity. And as the voltage gets higher, first, this accumulation part, the conductivity consists constantly. But when the depletion part, the conductivity goes down. And when the weak inversion starts, the conductivity goes up again. And when the strong inversion, the conductivity goes constant again. And we can call this part of 2 phi b. The 2 phi b means the intrinsic Fermi level minus Fermi level. For example, we drew a inversion state of energy band diagram. And Fermi level is here. But the intrinsic Fermi level is here like this. So this part is a intrinsic Fermi level minus Fermi level. So we can call this a phi b. And if the bias gives more than 2 phi b, the strong inversion starts because here and here is 2 phi b. So when the voltage gives more than 2 phi b, the strong inversion starts and the conductivity consists constantly again. So this is a Severy characteristic. So this time we learned about the MOSCAP device, and we also draw the MOSCAP band diagram, and we discuss about the relationship between conductivity and voltage bias.